All right, we're going to talk about applications of quadratic equations. Now, this first application is one of the most commonly used problems, not just in college algebra, but also it even extends into calculus. And when I taught Calc 3 last time, I even had an idea to use it for Calculus 3. So it's just a favorite application. It's a problem you're going to see over and over again if you continue doing math. Okay, and it's a fence along a river. Okay, so let's say we have a gardener. So our gardener has 200 meters of fence to enclose a rectangular region along a river. Okay, find the region with largest area. That can be enclosed. Okay, so let's go ahead and set up the problem. We're going to talk a little bit about quadratics and their maxes and mins. So actually, let's talk about quadratics and their maxes and mins first, real quick. Okay, so let's say we have a quadratic y equals a times x minus h squared plus k. All right, so sort of very informally, I'm not even going to make those straight. Okay, at hk, we have our vertex. And if a is bigger than 0, it looks like so. And we have a minimum value at the vertex. Likewise, if we have, let me copy this. Try that again. There we go. Now, if a, on the other hand, is less than 0, okay, then we have something that looks like so, and we have a maximum value at the vertex. Okay, and of course, if a equals to 0, we don't really have a quadratic equation. We have a linear equation. Okay, so let's go back to the problem with this sort of in mind. We have 200 meters of fencing to enclose a rectangular region along the river. So, draw our river. Okay, we have fencing. Okay, and we have the sides. Let's say this is y and this is x. Okay, so anytime you have a application problem, okay, this is what's called an optimization problem, actually. Okay, anytime you have an optimization problem, you want to try to find two things, okay? First thing you want to find is you want to find what is it that you're trying to optimize, okay? So what is it that I'm trying to optimize? We're collective here, so what are we trying to optimize? Okay, well, what we're trying to optimize here is the area, which is x times y, okay? The second thing that we have to ask ourselves is, what are our constraints? Okay, what is our constraint? Let me actually move this down. Okay, so what is our constraints? Let me move this over here. Okay, let me make this bigger too. Okay, what are our constraints? Our constraints are that we have 200 meters of fencing. Okay, so 200 meters of fencing, how does that translate into an algebraic equation? Okay, well, that means that x plus 2y equals 200, right? The perimeter of our figure equals 200, okay? So now we're going to insert our constraint into our area so that we can get a new equation of just one variable. So our area, which is x times y, but this equation means that x is 200 minus 2y, correct? So x times 200 minus 2y, sorry, 200 minus 2y times y is our area as a function of y. Let me expand that out. That is negative 2y squared plus 200y. Okay, but this is just a quadratic, isn't it? It's a quadratic with your coefficient of y squared being negative, so it's going to have a maximum. Where does the maximum occur? The maximum occurs, of course, at the vertex. Okay, in this case, it's a vertex, it's a equation in y. Y is not the y variable itself, it's y, so it's going to be y equals negative b over 2a, which is negative 200 over 2 times negative 2. Okay, our b is 200, our a is negative 2. So that's going to end up being negative 200 divided by 4 is 50. Okay, now if y is 50, then x, being 200 minus 2y, is 200 minus 100. That's 100. Now this is all in meters. So our area is actually going to be 50 meters times 100 meters, which is what? 5,000 meters squared. Okay? So that's the enclosing a rectangular region along a river problem, which is probably one of the most popular problems you will see in any sort of math class that you get. Okay? All right, we'll be back with one more application.